So hello, good morning everyone. Today I'll give a talk on the effects of regularization and smooth transition on the spectrum of primary gravitational waves. This talk is based on our ongoing collaboration, and this is a brief outline of my today's talk. That is, first I will discuss about the generation of perturbations during inflation, and then the essentials of the primary gravitational waves, mainly the power spectrum and the spectral energy density, and then what will be the behavior for the instantaneous transition from de-Sitter inflation to radiation domination. And then I will discuss about the adiabatic regularization and why do we need to regularize power spectrum and the ACD. And lastly, I will discuss about what will be the effects on the spectrum for smoothing the transition from de-Sitter inflation to radiation domination. I will conclude with a brief summary. So, inflation is an accelerated expansion at early universe, which is one of the plausible solution for the isotropic nature of the cosmic microwave background. In addition, the quantum vacuum fluctuations generate perturbations during inflation, and that sets the inhomogeneities observed in the CMB at the order of 10 to the power minus 5. This inhomogeneity is largely caused by the scalar perturbations, but during inflation, during inflation, the tensor perturbations also generates. And in this talk, we will largely restrict ourselves in the tensor perturbations because these tensor perturbations propagates through the universe in the form of primary gravitational waves. So the metric of the primary gravitational waves can be written in this form, and for this such kind of metric, we can get the perturb-Einstein equation and get the equation of motion for the tensor perturbation. And furthermore, as I said, this perturbation is generated due to the quantum vacuum fluctuations. So we need to quantize such tensor perturbation and rewrite the equation of motion in terms of Bukhanov-Sasaki variable. Now, for tensor perturbation, we need two observational quantity. One is tensor power spectrum, and another is spectral energy density. And for the tensor power spectrum is a 2-point correlation function in Fourier modes, and such tensor power spectrum can be expressed in terms of Bukhanov-Sasaki variable in this form. Now, to get the form of the spectral energy density, we can get the tensor perturbation action, the second order tensor perturbation action in this form, and from this action we can get the spectral energy density in terms of Mukhanov-Sasaki variable. Now, for the observational interest, we need to get the dimensionless quantity, that is spectral energy density, and with the ratio of the energy density and the critical energy density. And to get the value of omega GW today, it is well known that the tensor perturbations, energy density of the tensor perturbations falls as the power of a to the power minus 4, just like our radiation energy density of radiation domination, and we will get the value of today and get the value of today. Now, for a power law case during inflation, the scale factor is given by this, and we imposing the Burns-Davies initial condition in the Mukhanov-Sasaki equation, we can get the solution for the Mukhanov-Sasaki equation in terms of Hankel function. We restrict ourselves in the de-Sitter inflation, so we'll set the value of q equals to minus 1. Now, now we are assuming that there is an instantaneous transition from inflation to radiation domination, and in such a radiation domination, the scale factor is given by this, and for such a scale factor, we can solve the Mukhanov-Sasaki equation in this form, and this is the Mukhanov-Sasaki variable. And so for such a Mukhanov-Sasaki variable, we can express the power spectrum, and we can rewrite this power spectrum using the normalization constant, and where y equals to k by ke. And similarly, we can express the rho GW in terms of Mukhanov-Sasaki variable in the radiation domination, and it is well known in the literature that we need to time average this rho GW for our observational interest. So with respect to time, and also when we average this rho GW, all the oscillating term will vanish. The only remaining term will be this. Now we need to determine the coefficients value during the radiation domination, and to get that, firstly we need the coefficients of the scale factor AR and eta, and we can get those values from the continuity at the end of inflation of the Hubble parameter and the scale factor. And by that we can determine the eta r equals to 2 eta e and a r equals to L0 by eta square, eta e square. And like in similar way, we can match the modes, the inflationary modes and the radiation modes at the end of inflation and get the value of the coefficients alpha r and beta r. Now we just need to substitute these values alpha r and beta r in our previous expressions, and what we will get, the power spectrum will look like this and average rho GW will look like this. So you can see that at the YE much greater than 1 or the K much greater than KE, that is in the small scale limit, the power spectrum will behave in the YE square or in the K square, will show the K square rise, and the averaged rho GW will show a K to the power 4 rise. So this is the plot of our tensor power spectrum at the time of equality, and this is the spectral energy density plot today. Now there is a rise in the spectrum for the power spectrum and the rho GW for K greater than KE. So if this is true, then there is a problem because it will rise forever and eventually it will break the perturbation theory. So we need to regularize. One of the simplest regularization technique is the adiabatic regularization technique, and before going into depth, I will explain adiabatic regularization. So this is a time dependent harmonic oscillator. This looks like in a similar form of our Mukhanov-Sasaki equation, and for such a to solve this such equation, we can define some WKB answers, and if we substitute these answers into this differential equation, we will get this equation. And now if we can expand write this Wk in a series expansion by an iterative way, we can get all the orders of all the adiabatic orders. So we can show that all the first order and third order term will vanish, and all the 0th, 2nd and 4th order and the remaining even order terms will remain. Now for our interest, we need to regularize the power spectrum, we need only the up to 2nd order adiabatic terms, and for our Mukhanov-Sasaki like equation, the 0th order and 2nd order will look like this. Now the adiabatic contribution from the power spectrum will look like this, and so we need to now subtract from the exact expression of the power spectrum, and after doing this calculation we will get this, and now we need to substitute the beta value from the instantaneous transition, and if we substitute this value we will get this expression, and you can see in the leading order the scale in the small scale it will behave as a scale invariant. Similarly, we can get to regularize the rho GW, we need the 4th order. We already have a 0th order and 2nd order in the last slide. So the 4th order term will look like this, and the adiabatic contribution for the spectral energy density will look like this. And if we subtract from the exact expression, the regularized rho GW will be this. Now again, if we substitute the beta r, it will behave as scale invariant in the small scale. Now this is the blue one is the regularized spectrum, and you can see it's a scale invariant in the for the K greater than KE. Now what will happen if we smooth the transition from inflation to radiation? So one of the simplest way to smooth the transition is to smooth the effective potential in our Mukhanov-Sasaki equation, and we know that the effective potential will be in this inflation will be 2 by eta square, behave as 2 by eta square, and in radiation domination it will be 0. And one of the simplest function we can assume as a smoothing transition will be in the linear function. And for such a case, the scale factor equation will be this, and we can solve this equation. We can solve this equation in a general form in the ARE function. Now, this is a scale factor in the smoothing period, and what we can do, we can match the time derivative and the scale factor and the time derivative of the scale factor at the end of inflation and get the value of A1 and A2. Similarly, we can get the matching condition at the scale factor and the time derivative of scale factor and get the value of AR and eta r. So this is the behavior of our U eta or A double prime by A, and this is the behavior of the scale factor. Now in a similar fashion, we can match the mode of the smooth transition at the eta E and eta E plus delta eta. and we can again get the general solution for such a case in terms of Airy function, and we can match the modes at eta e and eta e plus delta eta and get the value for b1 and b2 and then the alpha r and beta r. So all we need to get the expression of alpha r and beta r and substitute in our previous equation. So after doing that, there is a long calculation. After doing a long calculation, we can get this exact expression of alpha r and beta r. This PS11 and PC11 are different linear combination of the Henkel function and the Airy functions. But the point is, this all are the function, all are dependent on the ye or the k. So what we can do before substituting this exact expression, we can analytically understand what will be the behavior in the small scale limit. So we can expand these things in the small scale limit and get the behavior of the alpha r, beta r, alpha r and beta r in the small scale limit, and after performing that we can see that in the small scale limit the beta r will behave as 1 by ye cube. So Okay, so I'm not going to able to go to the slide. So the beta is going as 1 over 1 e cube. So so rho gw will be 1 over y, so ye to the power 4 into the beta r squares, and beta r squared is behaving as y to the power 6. So our rho gw will behave as ye to the power minus 2. So in the small scale limit, it will behave as k to the power minus 2, and similarly we can show that in the power spectrum will show a k to the power minus 1 behavior for k greater than ke modes. So this is the plot for the power spectrum and the rho gw, and this is the summary of my talk. And the question is this unique, or we can, like, if we use different function, will it be the same behavior? Arnab will discuss in the next talk about that.
Okay, thank you, Tanmay. Quick questions.
Hi, thanks for the nice talk. So, if I remember correctly, for adiabatic regularization, you get a scale invariant
Yes.
spectrum, and then when you do the smoothing of the scale factor, you get k to the minus 2.
Yes, the rho gw will behave as k to the power minus 2.
Yeah. Do you have any intuition when you get like these two different behaviors?
So yes, after adiabatic regularization, it is giving just scale invariant, but because of this smoothing the transition, this suppression in the power at the for the k greater than k is coming. So why it is coming? Why this k to the power minus 2 or k to the power minus 1 behavior showing? The Arnab will discuss. It depends actually on the continuity of different points at the smooth transition.
Can come back to that, and then Rajiv, you had a question. Same. Okay, great.